In this problem, what we're going to be talking about, and in this video primarily, is simply how to draw Lewis dot structures. And this question says, draw the following Lewis dot structures for the following molecules. So the first one we have is we have formaldehyde. First thing we want to do is we want to count the number of valence electrons. So each hydrogen has 1, the carbon is going to have 4, and the oxygen is going to have 6. So that gives us 12 electrons that we have to account for. Now, we want to start with carbon will be the central atom, will be the most metallic. It's down and furthest to the left, even though hydrogen is sometimes on the periodic table is going to be placed to the left of carbon, but it's also above it as well too. And hydrogen is going to be a gas, carbon is a solid. Now, each hydrogen is bonded to a carbon, or each hydrogen is bonded to the carbon, and then the oxygen is going to be bonded to the carbon as well. Now there's going to be a double bond here, and if you calculate the formal charge of everything, you'll find that the formal charge of oxygen is 0, hydrogen is going to be 0, hydrogen is going to be 0, and carbon is going to be 0. If you're ever in doubt as to whether you have the correct formal charge or not, or whether you have the correct structure or not, you can always calculate the formal charge. That will tell you or assist you in determining whether you have the correct Lewis dot structure. And remember, the molecule that typically has the greatest electronegativity is going to have the negative charge. Now, there are going to be some examples of this. So, for instance, phosphorus hexafluoride, it's awfully hard for a fluoride. In that case, the fluorides will only have a single bond. The fluorides can't have more than one bond. The next one we have here is we have peroxide. And once again, we're going to count the number of valence electrons that the peroxide has. So this has 2 times 1 for each hydrogen, plus 2 times 6 for each oxygen. This is going to be 12 plus 2. This gives us 14 electrons. Now you may ask yourself, what's going to be the central atom here? Well, the central atom in this case is going to be the 2 oxygens as such. And so you can draw the peroxide as such. And so we start counting the number of electrons, 2, 4, 6, 8. 2, 4, sorry, I can't count. 2, 4, 6, 8, 10, 12, 14. So that gives us 14. Now notice, hydrogen is only going to have 2 electrons. There are the 2 electrons for the hydrogen. Each oxygen is going to have 8 electrons. So there's 2, 4, 6, 2, 4, 6, 8. And then the hydrogen is going to have 2 electrons as well. So let me go through that again. The hydrogen has 2 electrons. This oxygen has 2, 4, 6, 8. This oxygen has 2, 4, 6, 8. This hydrogen has 2. And so this is hydrogen peroxide. The peroxide is actually an O2 minus charge, is what the peroxide anion is. Now we're going to go to hexafluoroethane. We're going to count the number of valence electrons. And so each carbon atom has 4. Each fluorine has 7. And this gives us a total of 50 electrons. And the carbon atoms are going to be at the center. And the fluorines are going to surround the carbon single bond. And what I'm doing here is I'm simply just putting the valence electrons around each fluorine as such. Now, to make sure we have the 50 valence electrons that we're supposed to have, this is going to have 8. This is going to have 8. That's going to have 8. 8 more, 8 more, and 8 more. And so 2, 4, 6. 6 times 8 is 48, plus this pair right there is going to give us 50 electrons for hexafluoroethane. We have a few more examples here in which we're going to be finding the Lewis dot structure for. All right, so the first one is arsenite. This is going to be an anion that contains arsenic. And we want to, once again, come up with the number of formal charges, or not the formal charge, number of valence electrons. Arsenic is going to have 5 plus 3 times 6 for each oxygen. Now, because it's minus 3, we have 3 more electrons that we have to take into account. And this is going to give us 26 electrons. 26 electrons. We're going to start with the arsenic. At the central atom, we're going to have oxygens, 3 of them coming off of that. And so we can do this. Now this gives us 8, 8, and 8. 3 times 8 is 24. We have then 2 more for the 26. If we come with the formal charge of each oxygen is going to be minus 1, minus 1, minus 1. So this is going to be the correct structure. But let's just say, well, I want to show you something. If we put this pair of electrons in there, such that this now becomes a double bond, as such, this is going to have a formal charge of 0. So this one will have a formal charge of minus 1, minus 1. This will now have a formal charge of 0. If we then do the formal charge of arsenic, that is going to be 5 minus now 2 minus 1, 2, 3, 4, 4. And so this will have a formal charge of minus 1. Now, it makes more sense, though, that the minus 1 goes on to the oxygen and not the arsenic, because oxygen is going to have a larger electronegativity than arsenic will. And so what actually happens, or what is the more correct structure, is going to be this one, in which now the formal charge of each oxygen is going to be minus 1. Therefore, this entire molecule will have a charge of 3 minus. So you have a minus 1, minus 1, minus 1. This is now sulfurous acid. We're going to do the number of, we want to count the number of valence electrons that is going to be on, or is going to be incorporated into the sulfurous acid. So this is 2 times 1 for the hydrogen, plus 6 for the sulfur, plus 3 times 6 for the oxygen. This gives us 26 valence electrons as well. And the sulfur is going to be the central atom. So the sulfur is the central atom. I'll grab another marker. Sulfur is going to be the central atom. These oxygens are going to be, or these hydrogens are going to be bonded to the oxygens. So there's one, and then we would have another oxygen right there, which is going to be double bonded. Now, if we start counting the number of valence electrons here, oops, let me complete this. Getting a little ahead of myself. This would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So we're missing a pair of electrons onto the sulfur. If you want to calculate the formal charge of all this, the oxygens are going to be 0, 0, 0. We can calculate the formal charge of the sulfur, and that's going to be 6 minus 2. So sulfur has 6 valence electrons, minus 2 for the lone electrons, and then now 1, 2, 3, 4 bonds. And so this now is going to have a formal charge of 0. And so this seems to be a very, very good structure for sulfurous acid. Just erase this so we have a little bit more room for our last example. And once again, what I want you to do is I want you to calculate the number of valence electrons that is going to be in chloramine. So this is chloramine. It's an organic, inorganic molecule as well. And if we count the number of valence electrons, nitrogen has 5, plus 2 times each hydrogen has 1, plus 7. And so this is going to give us 14 electrons. The nitrogen is going to be the central atom here. And 1, 2, 3. This is a pretty easy molecule to draw as such. So now if we start counting the number of valence electrons here, we have 2, 4, 6, 8, 10, 12, 14. So this has now our 14 electrons that we were looking for.